good afternoon. So with James having covered diesel, I will now talk about some of the activities we have in the gasoline field. In the presentation, I will only very quickly cover the boundary conditions that have been driving to the development of GPFs. Then talk about GPFs, technology, how we see the current market introduction and ramp-up, architectures that we see, very quick on filtration, and then some section on some challenges that are coming along when you introduce something that is quite new, and most of them are related, for example, to ash and soot. These are things that have not been dealt with in the gasoline area, and I will kind of close with some of the experience we have made with a sort of a field trial we had within Corning, and then I will conclude. So we talked about, so this is on boundary conditions, is obviously regulation, and we talked a lot about Europe, so I think we have quite robust regulations for particulates, especially for GDI engines moving forward, starting later this year. What we've not talked about is also, like for us, it's China is an important market. Obviously, China will introduce also a particulate number limit, actually fuel neutral, so diesel and gasoline, not only GDI, but GDI and MPI. They also plan to introduce RDE regulations. The current compliance factor that is published is 2.1. And the current plan for nationwide in China is that the RDE monitoring and the introduction of China 6 will start in 2020, and then 2023 OEMs have to be RDE compliant. Now, besides these times, what we do expect, and you will see it later when I show when we expect the introduction, is that we do expect that several of the eastern provinces or cities, it used to be Beijing, probably also Shanghai and some of the other cities, they will introduce China 6 earlier. They will introduce pieces of China 6B earlier. It's not totally clear which parts they will introduce, but that is actually what is driving GPF introduction in China, as you will see. So we've seen many of this. So this is our version of emission tests that we've done on test vehicles we have in our fleet. And this is different GDI vehicles, MPI turbocharged, MPI turbocharged, and turbocharged GDI. We did testing in Europe. We do use local commercial fuel. So in Europe, that's close to Wiesbaden. Basically, that's where we get our fuel. We did some testing in China, in the Shanghai area. And I think the message has been already clear in all the previous talks. So we do see that, and for us it really is WLTC, so not WLTP, we just use a different cycle. We do use RTS as a surrogate for, like RDE as a more stringent drive profile that is easier for us for development purposes. And we see that I've added kind of the shaded areas for future RDE regulation in the two regions, that there are significant improvements needed from these vehicles, which are all not old vehicles, but they are kind of current vehicles, so they don't represent Euro 6 D vehicles. But there's a significant improvement needed to achieve the required particulate number emissions in the gasoline area. So what we see and what we kind of believe is that to kind of meet these future emissions, there's both needed. There is a reduction in the emissions that come from the combustion, from the engine needed. That's to manage the filter, but also to get the emissions into a range where then the filter can kind of take care of the rest. And then the second element, obviously, is the introduction of gasoline particulate filters, which we will see pretty much across all applications in Europe. I'm not sure who is familiar with gasoline particulate filters. So this is a picture of some of our technologies. So they basically look exactly like DPFs. If you just look at them, they are actually quite different. But we do use the normal honeycomb ceramic substrates. They are plugged in like a checkerboard pattern where every other channel is plugged on the inlet side, and then the other channels are plugged on the outlet side. You might see it here, you might not see. So basically that forces the exhaust gas entering the filter through the open channels. The gas cannot exit on the outlet side, so it is forced to flow through the filter wall, which is porous. Within the filter wall, then the filtration takes place, so particles are collected. What is, for those that are not familiar, important is it's not a sieving effect. We actually use a basic filtration based on different mechanisms. It's a Brownian diffusion for very small particles, interception for medium particles, and then for maybe it's usually negligible some inertia. So the particles are usually in nanometer scale, pore size is in the micrometer scale, so it's really not sieving. Compared to diesel particle filters, so again, as I said, they look similar. They are actually made, all of them, including competitive parts, of porous cordite ceramic. It's the same material as a ceramic that's used in the catalyst, in the three-way catalyst as a ceramic substrate today. That is different from light-duty DPFs. It's similar to heavy-duty DPFs. And then the design is basically designed for the unique requirements in the gasoline environment where we don't need to worry about very high soot loads, so we can optimize for low filtration and the appropriate for low back pressure and appropriate filtration. So for the introduction, this is kind of years, some of the key regions, and we have Europe here, and we see that and the green symbols are where we see GPF introduction. For Europe, basically this will start in September this year, so from September onward you will be able to get vehicles that have GPFs installed. For China, we are separating the cities or these eastern provinces and China nationwide, and we do expect introductions in the time frame of 2019-2020. So that is reasonably clear. What is kind of interesting is we've also added India and North America. So India has made the decision to move forward to Euro 6B type with the introduction of Bharat Stage 6, and by 2023 India also plans to introduce RDE. They also have the same, at that time they will have the same particulate number standard as we have in Europe, 6 times 10 to the power of 11. So there is some likelihood if India continues to stay on their path that they will actually introduce in this time frame also GPF in India. And the interesting part is that in North America, where the EPA and CARB still kind of maintain, first of all, a mass-based standard, and then a mass-based, it will now go to 3 milligram per mile. We're not sure that the GPFs would be needed. So particulate emissions compared to Europe will be higher in North America. And then only in 2025 to 2028, CARB, so California Air Resource Board, is starting to plan to introduce a lower particulate mass emissions. At that time, it will be very challenging to meet without the help of a filter. So the interesting part for us, we will see how that actually plays out, is that actually maybe we will see filters first in India before we see them in North America. So on the architecture, so James had similar pictures for diesel. This is what we see in the gasoline world. And before I describe the pictures, just this is sort of our pictorial of the architectures. The red is always the three-way catalyst, and then the component behind would be the GPF. There's green I always use for uncoated GPF, orange or yellow I use for coated GPFs. And then we do separate between components that are close coupled, so three-way catalyst is always close coupled to the engine to get the maximum of exhaust temperature. So we do have close coupled installations. We do have GPFs this should kind of show units that are underfloor. So they are just installed below the vehicle body. And what we do see is, first of all, the ramp up, it will start this year, so there's no numbers, this is millions of units and cars. And it will increase quite rapidly. Europe should be kind of saturated towards 2018-19, and the additional increase is basically that we start to see also volume in China. So this is China and Europe. It's kind of the global GPF ramp up. What is interesting is on the architectures, what we do see is there's probably 2/3 where people like to go close coupled. The simple reason is that close coupled temperatures are higher, so soot management, and I will discuss about that a little bit later, gets much easier when you close coupled. The challenge is there's usually no space, so that's why some people go underfloor. So this is easier to retrofit to an existing system. This is much more challenging. And then what we do see in these close coupled, there will be some section, I think it doesn't look like, but it's almost 20% will be without coating on the filter. So it's just a filter that is added. The catalyst remains unchanged or with an improved catalyst formulation. Some will be close coupled, some will be fully integrated. And then there will be some segment with the underfloor catalysts. At the beginning, actually not insignificant. Since the requirements for the filters are quite different if you put a catalyst onto a filter, or like in this case, or you just use the filter, which is kind of from design here, we have to consider that we have to optimize not only for filtration back pressure, but also for the catalyst coating. If there's no catalyst, we can basically optimize for filtration and pressure drop. So it does require very different filter technologies. So we've developed 2 families. They are all commercialized under our brand name DuraTrap. The first family we call the GC, that's gasoline, that's chloride. It's in the 200 CPSI 8 mil web thickness design. It has a medium porosity and it's usually used without coating or maybe a light catalyst coating. The other family we call GCHP, which means high porosity. It has a little bit higher cell density. That's just to enable better performance of the catalyst that is applied to these. And the porosity is much higher, 65%. That's, for those who are involved with this design, is actually quite challenging to get good mechanical strength. The porosity is mostly higher to enable the catalyst coating to kind of be integrated into the filter without having extreme back pressure. So this is basically designed to enable all the currently planned catalyst quantities. So just some examples on filtration, and there's not much detail I want to kind of discuss. So these are 4 different vehicles from our test fleet. There's all different architectures. Some are close coupled, some are underfloor. Always tested over NEC, WLTC, and RTS 95. And first look at in different filter technologies too. So this is what we typically see for GPF. We see filtration efficiency. So these are PN filtration efficiency in the range of 70 to 80% efficiency. And that is what we typically can expect because we basically have no soot in the filter. So this is what physics allow us to do with something that has a pressure drop as designed, and that's what the systems will be designed for. This is one example. It's an underfloor installation where we actually get quite high filtration efficiencies. They're not as high as diesel, but they're close. And this is one case where it's an engine that has pretty high raw emissions and very low temperature. So we actually always have some soot, and it is always there. So that is boosting filtration efficiency more closer to the diesel area. But this is just some examples, and that's what we typically would get. These are all fresh filters, so they don't have a high mileage. Since there is discussion moving forward that, so today particles are counted starting at 23 nanometers, that was defined during the PMP work. And there's some discussions that kind of question if that's okay or if we should also include smaller particles, as we actually, especially in the gasoline side, might see some. So we've done some testing on, this is just one example from one of our vehicles where we've done normal testing. It's again NDC, WLTC. And we've done the normal testing using a CPC with the volatile particle remover, just the normal PMP method. And in parallel, we've done also, doing the same test measurement with using a DMS 500. It's equipment that can also measure particle size, so we can analyze also for the contribution from smaller particles. And basically in this picture are shown the emissions from the vehicle just with that's how you would buy it, just 3-way catalyst only, so no filter. PN, and then you basically see that in blue are the values from the DMS 500 for the accumulation mode. So these are the larger particles, and it matches actually quite nice with the way we currently would measure for regulated, following the regulated procedure. And then green are the particles that are actually smaller. So this would be the nucleation mode. So these are really small particles. And what we see, they basically come additive. It's a log scale, so it's not so easy to say how much it is, so we've added these little pie charts. So it's about 25% more particles just by number that you would add. I've seen higher numbers on other vehicles, but this is the case for this vehicle. And what we've then done is we basically took the same vehicle and added the GPF. It's a coated GPF, close coupled 2-position, done the same tests, and these are the results. And again, you can see the normal particles as we measure today, as well as the small particles are all well removed. This is kind of the same data. This is particle size distribution. This is the size. This would be cumulative number. The black line is just a 3-way catalyst, so this would be this. This is the line with the GPF for the WLTC data. These are like cumulative size distribution over the entire cycle. So it's not at any specific time, but it's cumulative. And we basically see that we also remove basically the filter removes particles over the entire size range. So it's a robust solution. So this was the good thing. This is why we would install a GPF, so it has to remove soot particles or reduce particles to reduce our tailpipe particulate emissions. And there are challenges with that because the filter is not, well, it removes basically all the particles that are coming. Soot particles are kind of the easy ones because we can regenerate, we can keep burning them from time to time, or in gasoline they probably will burn by themselves from time to time. But the filter also catches ash particles, so these are usually inorganic components that are in the mostly lubricant additives, and we don't get rid of them. Once they are trapped over the life of the filter. And so basically this is just one example. These are 3 test vehicles from our durability programs. This is ash mass in grams versus mileage. So this is up to 200,000, these two are to 100,000. And as you see, as we increase mileage, basically we keep accumulating this ash. And the amount, these are actually, this is like super low oil consumption, this is medium. We've seen more. But basically the quantity is somehow related to the ash content in the oil, to the oil consumption and other factors. But it will happen. So by itself, not a big problem, it's not a huge quantity, and there's actually something that is a nice side effect. So this shows PN filtration efficiency versus this ash mass. So this will be this axis plotted here. And we see these are similar to the values from the previous slide. You know, even after a very short time with a little bit of ash, we do see the filtration actually improving significantly. And that is basically the ash forms a very fine membrane, it has very small particles, very effective collectors. And you know, after some mileage, which means some gram of ash, we get very high filtration efficiency. So that is actually kind of a nice feature because usually most engines tend to drift in the other direction, and so that is sort of acting counter to any potential engine drift. It does not come without a price, and basically this shows pressure drop versus, again, the mileage accumulation for these 3 filters. This one doesn't increase too much, although it probably is actually more the scale that doesn't look it, but pressure drop will increase. So we are adding an additional resistance that is something that the vehicle or engine will experience over life, and that is something that has to be considered during the design and also the implementation. So we have a lot of programs on understanding ash and the effect on the use in application. And it takes a long time to collect data. The other challenge is soot. So like in diesel, you know, there's probably half of the effort is actually to manage soot so that you don't destroy the filter. So the soot is collected. You know, if you collect too much, you need to get rid of it, so you have to kind of burn it. And this is so I've tried to kind of come up with something that's sort of schematic for gasoline to show there's some applications that are easy, some are more challenging. And if we kind of simplify it, we can probably break it into 2 main factors. One is the soot accumulation rate, so this is the amount of soot that is, it's coming into the filter. It will be high if we have an engine that makes a lot of particulates, so high engine out emissions. That's usually low temperatures, very short trips, frequent start-stops. Low would be low engine out emissions, so clean engines, mild temperatures, long trips. So this is how much soot we put into the filter, and then the y-axis here would be the amount of soot that burns passively. So passive means there's no strategy, it just happens as you drive. And that is high. For example, if we have high exhaust temperatures, this is one reason why you go close coupled, for example. You have always higher temperatures, maybe 100 degrees Celsius higher. And then to burn, you need something to oxidize, so that is air. Gasoline, we have usually lambda 1, no oxygen, not air, you need oxygen. You have no oxygen in lambda 1, but there are fuel cuts. This is when you kind of get off the pedal and then the vehicle is motoring and you're pushing fresh air into the exhaust that provides oxygen. So frequent fuel cuts, high temperature is favoring passive soot oxidation, and the opposite is kind of causing challenges. And then the colors basically just should show this is easy, this is really difficult because we burn very little soot and we are entraining a lot of soot. So this might lead into areas where active strategies could be needed, which nobody really wants to do. Now, I've added this little cartoon. So compared to DPF, we're in a totally different world. So this will be DPF is sort of as a cartoon here is DPF. We have 10 to 100 times more soot from a diesel engine compared to gasoline. And the conditions under which you can burn soot passively in gasoline are almost none. So it's a very different world, diesel to gasoline, but you still have to kind of consider it. I will now show on the next slides a couple of examples from our test vehicles. And our test vehicles, and this is only qualitative, but they're kind of in these areas. So this will be the vehicle fleet that I show later on. Typically, we have operating conditions that are quite favorable. It's company cars. These are 3 test vehicles I will show sun data. We have none. It's really super challenging, but nevertheless, I think these will kind of serve to show the idea. So this is now these three vehicles, vehicle A, B, C. And what is plotted in all of these is the temperature at the filter, and there's always two lines. So these are dedicated test runs that we do. Here it's always, the scale goes to 1,500 kilometers. So this is all city driving, so it's actually, we're talking about days into weeks. And the two lines are, this is the temperature at the filter. This is the maximum temperature observed during one shift. Usually we do 8 or 2 shifts, depending on how we operate, 8 or 15 hours per day. So this is the maximum temperature we have seen. And then the main objective was, will soot burn passively, or do we have to do, or would the application need to do something active? So these vehicles do not have any active strategy, so they just accept whatever happens. And since we've not been very successful in soot loading on a vehicle, because the emission rates are quite low, we actually do something different to study this. We basically soot load ex situ, so we take the filter, we put a lot of soot into it, what we think is a very high load. We put it onto the vehicle, and then we monitor the weight of the amount of soot in the filter as we, do our test run. So this is shown in this lower diagram. So the circles are the soot mass. They're determined by just weighing the filter. So this is 6 grams. Doesn't sound like much, but for soot, it's actually quite a bit. And then the lines are, in this case, simulations. So we use basically the second-by-second data. We have quite good, robust kinetics for soot oxidation and reasonable engine models. So we can simulate quite okay. So the interesting part was this vehicle the exhaust temperatures are extremely low. So in the diesel world, we would have said at these temperatures, soot can never burn. And but what we see is that even in this case, soot is actually decreasing. It takes a long time, but it will decrease. And the reason that it decreases, although temperatures are very low, is that this is a very clean engine. This was the cleanest I think we've had in our fleet. So it is on NEDC 1 × 10⁻11, just raw emissions. And so there's not much soot coming. So the rate of soot burning is very slow, but it still is higher than the rate at which particles are kind of re-fed into the system. So it does work. It takes a lot of time, but it is kind of working passively. Vehicle B still has quite low raw emissions, but the temperatures are a little bit higher. And you can see the slope is almost similar, so kind of higher. So we are kind of balancing between having a little bit higher temperature, so the rates are higher, but we also have a little bit higher entrainment rate. Now vehicle C is what is that is the more challenging. I put it somewhere here. This is a vehicle that has pretty high raw emissions, so it's 2.5 × 10⁻12. So this is like more than 20 times more than this one. This is where most Euro 5 GDI vehicles have been in this range. And the temperature is also low, so this is also underfloor quite far, and same for the temperatures, but the spread is a little bit higher. It's a small engine on a fairly big car, so it has to work from time to time a little bit harder. But when you look at the soot, again, we start at a similar level, it actually is increasing in use. So this is because now we are in an area where the amount of soot that we feed into the filter is actually higher than the amount that we can burn passively in the city mode operation. What we've done is, after some time, we basically changed our driving profile and said to the drivers, you can now drive up to 70 kilometers per hour. So not as an average, but up to as a maximum speed, and as a result the temperature increased a little bit, and now we get it back kind of under control. But this is sort of one example where the application can be challenging, and then either you need a strategy or you kind of have to work on the raw emissions to make it actually possible. So this is another challenge. So another thing we have to consider is we have to protect the filter that it's not destroyed, because if we have too much soot, then we get a very aggressive soot burning event, can get really hot in a filter. And basically to manage the soot, not to just keep burning it, but under severe conditions, usually look at the balance between the heat that is released, so it's in equations here, but it's released during the oxidation of soot, exothermic reaction, and the heat that can be removed by convection by the exhaust gas. And this is the flow rate is just given by whatever the vehicle is operating, but the rate at which it's oxidized is high. When the soot load is high, a lot of fuel, the temperature is high, very high rate, and there's enough oxygen. So in gasoline, lambda 1, we have high temperature, we might have high soot, but we have no oxygen. But as I said before, during fuel cuts, we actually can have everything. If it was high soot load before, high temperature before the fuel cut, then we get a flush with oxygen. And this is what we do to kind of do robustness testing. So we do on engine bench, it's quite tiny, but basically we are preloading a filter with soot. We are heating it at lambda 1 to a target temperature. It's about 800 degrees. In this case, it's quite hot for like a close coupled position. And then we introduce a fuel cut. This is 60 seconds. It's quite long because usually, you would probably start to kind of, either change gears or something. And as you can see, this is the maximum temperature filter. It actually gets hot. And when you look at this, this is, can do all sorts of testing with GPF. So this is the maximum temperature. Usually we are recommending to not go higher than 1100 degrees Celsius. The filter probably can handle a little bit more, but that's a quite good target to shoot for. This is the soot load in the filter, and the different lines basically represent data at different initial temperatures. So this is this temperature. So this would be like underflow is different than close coupled and the condition before. And roughly we see an increase of about it's roughly linear 80 Kelvin per gram per liter, and that kind of defines how much soot we can have at maximum in the application. So that's an application target that the engineers at OEMs have to take care of. And from our side, we have to make sure that the filter is robust, so we basically do repeated such events. So this is maximum temperature, and we do that a couple of times in a row, in this case 10. And we check for filtration efficiency always after that the filter doesn't lose the efficiency. So the last is, so we kind of done all that in parallel, and then we have this fleet experiment where we took 12 company cars that we actually told people that they have to get a GDI vehicle, which is not common for company cars. And they were all first registration 2014 and a little bit later. We all retrofitted them with GPF. These are just pictures from them. The cumulative mileage we had, the experiment is finished, was a little bit more than 650,000 kilometers. For the design, we used, this is volume to engine displacement, this rough ratio of 1:1, 1 liter engine, 1 liter filter, 2 liter engine, 2 liter filter as a rough guidance. We try to have, for higher power cars, larger frontal area that's good for pressure drop, so you don't lose too much power. And then we tested fresh emissions, so the empty symbols are the vehicles as we had them, and then with the filled symbols is with the GPF, so obviously we see the expected reduction. These are CO2 emissions measured over NEC WTC cycle before and after the retrofit. We've not seen anything that we can actually measure in our tests. And then the next slide is sort of the summary. So we've done that for like 2 years, and these are emission data measured throughout the program. The program is stopped, so you can see some filters had almost 100,000 in this case. Some had a little bit less. For all of them, we see emissions quite low, and we also see this kind of evolution towards lower values as we go. And there were no complaints from kind of our drivers or the operators of the vehicles. There was nothing we kind of did. From an operating profile, it has been mentioned, it's what I had before on the red-green chart. They are all quite easy. They're company cars, so they see fairly high temperatures quite frequently. So with that, I want to close. So to summarize, there are advanced regulations that are kind of, requiring to reduce particulate numbers of gasoline cars significantly. Gasoline particulate filters are one technology. I think they still need the changes in engine raw emissions, but they kind of quite robustly reduce particulate emissions. We've developed different technologies. They're all based on chloride ceramic wall flow filters. The design has been optimized for GPF, for gasoline applications versus DPF. And there's different technologies for filters, uncoated, coated. There's challenges that come with the introduction of a new component. We've tried to do some of our work to help understand some of them, how to address them. They're similar to DPF, but they're different to DPF. So there are some of the things we can use from the learnings made in diesel side. Some of them are really, really new. So far, our experience with everything that we've done operating company cars or test vehicles, we have also multiple vehicles now to more than 100,000 to 240,000 kilometers, has been quite positive. That I close, and I'm also open for questions. Thank you.
Thank you very much. Before I open for questions, of course, anyone has a question, just raise your hand. Just a practical information. We have decided to change a bit the order of the next things. We are going to have the 2 next presentations right after this one, and then a closing networking break after the presentations. There are a few people who have earlier flights and asked us to finish the presentations a bit earlier. So when this presentation finishes, just stay in the room, and then we'll continue with the next presentation. Great, so does anyone have questions? Okay, there's one here. Okay, and there's a comment here, question here. Yes.
Thank you, Mr. Boger, for a very interesting talk. My question is if you have experience also with petrol hybrid vehicles, or if you foresee problems here. I'm thinking of, you have the engine turned on for short times, and maybe you don't get the fuel cuts in the same way because instead of having the engine on, you turn the engine off. And your thoughts on that? Thank you.
So we don't have experience. We are getting our first hybrid vehicle, I think, as we speak. In general, we don't expect the challenges, but I think what you just said was like, instead of fuel cuts, you are recuperating. And so that is something that has to be considered, and because without the fuel cuts, basically, there's no oxidant that can kind of reduce the soot. I think a benefit from the hybrid side could be maybe you can reduce some of your raw emissions by what is it, phlegmatization, I think was the word I was kind of taught, basically taking out some of the transients from the combustion engine and changing that to the electric motor. But no, I agree. So I mean, the first main concern would be if all fuel cuts are used for recuperating, then it might become a challenge for the soot management.
Yeah. And one in the front.
I think by now it's obligatory to have a question from me. So, very interesting results, of course, and thanks for the good words about the European Commission being the first to introduce GPFs. Can you go a slide back, maybe?
Yes.
Yeah. I mean, it's clear, you see clearly that the emissions drop off after the first kilometers, because it's clear that a green filter will have a different behavior than a H1. Most of the experiments and the results you showed earlier, however, if I understood correctly, were done with green GPFs.
Kind of green, so kind of green. We have very few did on 0-0. That's just a practical challenge. Our emission test facility is at some distance from our mechanical shop, but they are almost green. So we usually have 100 kilometers that we have on the filter. So that's not sufficient to generate any ash membrane. But we've done some on green, but most of them have a little bit. But it's not, you cannot see it on this scale. So here the first data point is fresh. The second was 3,000. The third is somewhere between 6 and 9, I think. So for this program, we did the fresh, which is 100 for us, 3 and 9 to see this evolution kind of.
Okay, but
so there is some improvement over the first couple of thousand kilometers.
Yeah, which is good, but my question had to do, for instance, when we are going to see in-service conformity these vehicles. They will not be green. They
Clean,
will
fresh,
be,
yeah.
Clean, fresh. So we would expect to see even lower values.
But similar to the values we've shown. I think our conditioning is the 100 kilometers does not make a difference.
Okay.
Yeah, but 2,000 would make a difference. I think one difference was also that what we had in the very early in GPF was that for catalyst aging, you never test fresh, you test always aged. So you're always like, for the filter, you're in the best case. And kind of for us, for the filter, we always test fresh, which is useless from the catalyst perspective. So it's two types of testing that has to be done.
Of course. And sorry, I think I have a thing behind. And there is a second question. I have to pose it. You have shown results for multi-point injection also.
Raw emissions. Only raw emissions, not with the filter.
Yes, raw emissions. they're surprisingly high, because I have to make this statement. When we set the Euro 5, Euro 6 limits, these results were much, much lower. And this is a point that we will be taking a close look in the upcoming legislation. I'm just warning everybody.
Sure, thank you. Okay, great. In this case, thank you very much again, Thorsten.